So there are a few different kinds of imaging modes. You have your amplitude mode, you have your brightness mode, you have your color flow mode, you have your Doppler mode, and you have your M motion mode. And then any combinations of the above will lead to the terminology of either a duplex or a triplex ultrasound. A duplex mode will mean that there's either a brightness mode or a B mode and a color flow mode brought together in one screen. So if you can have that, both modes active in one screen, then you have a duplex ultrasound machine. But if you have a B mode and a color flow mode and a Doppler mode all together working in the display mode, then you have a triplex mode machine. And this requires a lot of computing power for the ultrasound to be able to display this into the monitor. So the A mode imaging system is the simplest. Basically, you have here a transmission of the impulse, and then you have the reflection of the impulse of the different structures. And so the intensity of the echoes are just displayed as intensity of light. So you will see here that the intensities of the lights are seen at different distances because there is a structure. For example, the structure of the skin, and then the organ of interest, and then the spine, and then there's the in-between retroperitoneal tissue. And then you will see these these amplitudes, which will tell us that the echoes here are bright, the echo here is not so bright, the echo here is not so bright, and this one, the echo here, is a bit bright coming from the bone. And these are the waveforms that were picked up by the echoes. And you will see this bright lights in the ultrasound echo monitor. The main benefit of this is that you can measure the distances of these amplitude signals so that you will know what their relative distances are to each other. The B mode imaging system is the brightness mode, is basically a series of A modes brought together. Now, there is a sweep of the different A modes brought together, and then you will see a two-dimensional grayscale of the reflections of the structures of that pass through the ultrasound beam. So with that, you will see that there are higher intensity echoes, lower intensity echoes, no echoes, and putting them all together, you will be able to see what is called the grayscale. So this is the grayscale of the B mode, and the grayscale can have as much as 256 grayscales, points of intensities, or even higher, 512 or even higher. The cheaper ones will only have about 128 grayscales, which will not give you too much good resolution. But in general, having 256 to 512 is okay, different shades of gray. All right. Now, the M mode is again also a combination of the A mode and the B mode, except there is now the element or the dimension of time. When there is a movement, during movement, so when this organ is moving and the echoes are being transmitted at the relative changes in position of this moving echo, then if you run that across the dimension of time, you will see here the movement of the organ of interest elongated across a time dimension. So this is pretty much used in many self-moving organs. For example, the heart as the heart is beating, you're able to see the movement of the valves, the movement of the ventricles and the atria, and you will see them plotted against a longitudinal axis of time. And looking at the waveforms, you will see whether the valves are closing properly or moving adequately, or if the contraction of the ventricles are adequate or not according to the norms set by thousands of previous studies. Now, before we go to the color flow mode or the Doppler mode, we need to know what is the Doppler effect. The Doppler effect is what we usually hear when there is movement, and for example, the source of the sound is emanating from this moving object. Since sound travels, or the speed of sound is constant, if the object is moving with the source of the sound, the velocity of sound is not additive to the velocity of the source. So if the source is moving, then it will tend to compress the sound waves ahead of it because of its velocity. So if there is a compression of the sound waves in front of the moving object, then you will see that the frequency of the sound in front of the object is higher than the frequency of the sound at the rear of the object. And this changes the pitch of the sound. So you will hear that the sound, as it comes to you, as the object is approaching you, the frequency is higher, so the pitch is higher. And then as it passes you, the sound pitch becomes lower. Such like it goes like, it's like a whoosh. No? When you watch racing cars or the train or an ambulance going, passing you, you will hear the siren going at a higher pitch and then becoming lower as it passes you. That is called the Doppler effect. It also happens if the source of the sound is stationary and there is an object that is going towards the transmission of sound. And when they meet and the echo is transmitted back to the transducer, then that will have a higher frequency compared to the echoes at the back of that particle. So that is the principle of the Doppler effect in ultrasound. If you have a stationary transducer, the velocity of the sound as it is transmitted will be the same velocity as it is reflected. If you have a structure, for example, a red blood cell that is moving towards the transmitter emitted a certain frequency and then will receive the echo that is of a higher frequency because it is moving towards the transducer. If this red blood cell, for example, is moving away from the transducer, then the velocity as it is transmitted and hits the moving object that is moving away from the transducer, the reflection is going to be a slower or a lower frequency. So that is the Doppler effect. And for Doppler geometry, of course, for maximum Doppler effect, you need to have the beam really parallel to the direction of the flow. But it is kind of impossible to put a ultrasonic transducer at the end of a blood vessel like this, end to end, in order to get the ideal Doppler angle. So suffice it to say that the most acceptable Doppler angle that is by convention agreed upon is to hit the moving particles at 60 degrees angle. And this is the agreed upon angle for the Doppler geometry, for that the computer can compute and make extrapolations or interpolations as to the actual velocity of the moving red blood cells or the moving particles using this Doppler equation. We will not go into this into detail, just understand that there is such a Doppler equation that is fitted into the CPU so that the machine will be able to interpret and extrapolate the actual velocities using the equation. Okay, this slide just shows you that the Doppler angle dependence. So ideally, we want this angle at a parallel to the direction of flow. But since we cannot do that, we want it at 60 degrees as a maximum acceptable. Any more than that, going at 90 degrees, that's unacceptable because you will not be able to really see accurately the velocity as the red blood cells move away from or towards the transducer. So this is, again, the ultrasound system. Transducer, transmitter, receiver, detection, beam mode, scan conversion to the monitor. And this different frequencies by the different Fouriers or the different Dopplers are picked up and plotted along the waveform. And using the principle of fast Fourier transform, we now come up with a waveform that is actually a demonstration of the different frequencies and the velocities detected by the transducer. So the highest frequencies or the highest velocities will be at the top of the waveform, and the lowest frequencies will be at the baseline at 0. And then if you have particles moving away from then the transducer, then you will have a negative deflection in the waveform. And so there, with that, we now come to the discussion on color flow mode. Color flow mode depends on Doppler because it will tell you, it shows in the monitor qualitatively with the intensity, or semi-quantitatively with the intensity of the color, the velocity of the movement of the particle, and thereby the frequency of the vibrations. So when you have this color flow mode, it's not actually because of the color of the content, of the organ being examined, but it's really more of the color arbitrarily set by ultrasound manufacturers for certain frequencies and certain velocities. The blue, it can be set as a direction of a movement away from the transducer, and the red can be set as the movement going towards the transducer. So by a convention, if you have an arterial flow, they just set the direction of flow so that the Doppler color is set to red, and the color direction is set to blue for the veins, because we do know that their directions are generally opposite to each other. So that is what is called color flow scanning. Now, power Doppler does not take into consideration the direction of the flow, but only the intensity or the speed of the particles, and also the rate or the frequency rate of the particles. So the higher the frequency, the more intense the color, but there's only one color. It will not tell you the direction of the flow. Okay, now this image now shows us what is called the triplex using the power mode. Triplex because there is a B mode or the grayscale mode. There is a power flow mode, Remember, there's only just one color because of the power flow mode, but it gives us the intensity or the velocity of flow. And you have here at the bottom the Doppler frequency spectrum. Now, it is said here that this is the velocity, but this is pretty much the highest frequency, and this is the lowest frequency, and this is the negative frequency, which says that these are the particles or the frequencies that are moving away from the transducer. So this is now the triplex mode. Now be wary when your ultrasound company will try to sell you a machine that she will claim to have, or he or she will claim to have triplex mode, and will show you this image. Some machines are not really duplex modes or triplex modes, but they will have this kind of image. Why? Because the B mode is actually just a frozen image. The power mode is also just a frozen image. And the only image that is moving is the spectral Doppler, the Doppler mode. So that is not even a duplex. That is just a single mode display, because only one mode is active. For triplex to occur, you have to have an active real-time movement of your Doppler. You have to have an active real-time movement of your B mode, and you have to have an actual real-time movement of your power flow mode. And that requires a lot of computing power, and that's why triplex machines come at a very expensive price. If you have a triplex with a color flow mode, then you will have a machine that will give you the bidirectional indicator, no, of a red and a blue. And you will still also have the grayscale, and you will also still have the frequency mode spectrum, all moving in real time at the same time as your triplex machine. And finally, you will have here what is called the 3D and 4D ultrasound, which is really not just a duplex, but these are really a more computing power applied to two-dimensional images, that you create a sweep and it creates a 3D image. If the 3D image is static, then that is just a 3D ultrasound. So here you have a 2D ultrasound, and now you have these 3D static images. But if you add here now movement to the 3D, then you will have a 4D ultrasound. Now, if you rotate the 3D, that is still not 4D, because this is frozen in time. This is just still a still picture, frozen in time. But the 4D ultrasound is one that shows you actual movements in a 3D environment. So here is the 4D ultrasound, and you are actually seeing movement in 4 dimensions, and you can get machines with very, very strong computing power that can display the ultrasound images in 4D. Okay, to summarize, for the fundamentals of ultrasound and the fundamental physics, we talked about pressure, the physics of sound, how sound behaves, the characteristics of sound, the properties of sound, the properties of media that affect its acoustic characteristics. And then we talked about the transducer, which transmits and receives the sound. And we talked about the beam anatomy and the beam theory. And then we talked about how the beam is then computed, by using certain assumptions on the acoustic velocities and the length of and the depth, and how to adjust the images so that you will get better resolution, so you will get better signals, how to use your probe so that the processing unit will be able to have a better processing of the data that came in. And finally, we looked at how this data is then displayed either through loudspeakers or through the monitor using the different modes of A mode, B mode, C mode, D mode, and M mode. Well, with that, we end this lecture on the basic physics and basic fundamentals of ultrasound. And I applaud you for joining this course, because we now know that ultrasound is really an essential aspect in our surgical practices. And doing this, we can now do ultrasound as a point of care in the field anywhere we do our procedures, in the emergency department, in the operating room, even in our clinics, and of course in our laboratories. And ultrasound has become such an essential tool, such that it is now being used in the field, in the military, and in the waypoints, no, of Mount Everest, no, in extreme environments, up to even the space shuttle in the maintenance of health of the astronauts living there for extended periods of time. So with that, I would like to thank the organizers for inviting me to give this lecture to you. And I again congratulate you for taking the first step in learning how to use ultrasounds in your clinical practice. Thank you and stay safe.